Hi guys. Hi everyone. So hi everyone, welcome back to Introduction to Machine Learning. This is part 1. We had a slight technical issue, so we created another live video. So in this one, we'll go deep into machine learning, and then after that I'm going to share code with you so that you can go through it. And yeah, if you have any questions, feel free to ask on the live chat and I will be happy to answer. Cool. So we are doing machine learning deep dive module 2. So we have gone through introduction to data science and machine learning, as well as data wrangling and exploratory data analysis. Now we're going to get into machine learning. So in this module, we're going to talk about model development, so defining the machine learning task, supervised versus unsupervised learning methods, which we had briefly talked about earlier, measuring performance of your model, as well as validating your model. Cool. So here we are at modeling phase. So in the previous video, we talked about data cleaning, exploratory data analysis. We defined our research questions, so which was how does loan amount requested vary by town? And then now we're going to talk about modeling, how we get to modeling our machine learning model. So there are 2 steps to define the machine learning task and understanding how the machine learning learns. We will discuss model performance in the next module if we have enough time. So let's start with the basics. Why do we want to build a machine learning model? Why do we want to build a model rather? Machine learning allows us to tackle tasks that are too difficult to code all possible approaches on our own. So one of the definitions of machine learning is building a model that can learn without being explicitly coded. So we don't really have to write the same code all over again to do the same task. So machine learning allows us to do that. So yeah. So machine learning models quantify and learn the patterns we observe in data. So humans observe data, make assumptions from data. A machine learning model learns from the data that we have observed and quantifies it as well as predict outcome using it. Yeah. So we talked about three tasks in the model today is the defining the tasks. So what problem do we want our model to solve? Defining our learning methodology, whether it's supervised or unsupervised, and measuring how our model is performing. So there are various ways you can use an ROC curve, etc. So today we will be looking closer at each component of the framework. So task, what is the problem we want our model to solve? Defining effects. Effects is the function that will map our input, that is the data that we feed our model, as close as possible to the true Y output, as close as possible to the labeled outputs Y. This is usually in the supervised learning models. So next we are going to do some feature engineering. So feature engineering is basically it's mostly in during the exploratory phase, but it can also be done after you've modeled and you want to refine our model and make it better. So we need to extract some more features in our data. Yeah. So we decide what to include in our model. So is our FX correct for this problem? So what assumptions does our model make about the data? Do we have to transform the data? Is our model work? Is our model great? So that's where we check model performance. So learning methodology. So this is where we define whether our model is supervised or unsupervised. So how does the model learn the function that best maps X, that is the features, to true Y, which is the output variable. So we usually have the input variables. So that is what the model uses to learn, and then we have the output, what the model predicts. Yeah. So our model. So we first check whether our model is supervised or unsupervised. How does that affect the learning process? How does our machine learning model learn? So we'll go through an overview of how the model teaches itself. What is our loss function? And how or what is our loss function? Every supervised model has a loss function. The loss function is how what's the difference between what our model has predicted and what was the actual value. So optimization, how does the model minimize the loss function? So loss function is the difference between the actual value and what we have predicted. We talk about the training test sets there. So performance, how do we evaluate how useful the model and how it's learning is very essential. Satisfying results when evaluated using a metric, let's say accuracy score, but may give poor results when evaluated against other metrics. So most of the times we use classification accuracy to measure the performance of a model. However, it is not enough to truly judge our model. So we use R-squared, adjusted R-squared, and mean squared error. We also, for checking feature performance, we use statistical significance and p-values, and the ability to generalize to unseen data, overfitting, underfitting, bias, and variance. So R-squared is a statistical measure of how close the data is to the fitted regression line. So it's mostly used in linear regression. Adjusted R is a modified version of R-squared that has been adjusted for the number of predictions in the model. The mean squared is the average of the square of errors. So an error is the difference between what has been predicted and the actual values. and then from that you get the square, the square of the errors, and then you get the average. That's the mean squared error. We'll talk about that later. There's also overfitting and underfitting. So next we're going to talk about, so wait, before we get there, disclosure. For the next few slides, we'll be introducing the intuition between models using supervised learning examples. Later in this module, we will explore how unsupervised learning is different from supervised learning. So like I had mentioned before, supervised learning, we have labeled our Y. We have labeled data, and in unsupervised learning, there is no labeled data. We don't have Y in our variables. So back to our research question: how does loan amount requested on Kiva vary by town in Kenya? We have Kiva data about loan amount requested by borrowers all over Kenya, and we want to know how the loan amount requested varies by town. So building a model involves turning your research question into a machine learning question. So our question: how does loan amount requested vary on Kiva vary by town? So in machine learning terms, how would they put that? So let's go back a little bit and try to understand what features and observations are. So features are the variables that are on the, which are columns or on our columns. So that's lender account, lender amount, location, country, etc. Observations are usually on the rows. So location town is an example of a feature. Every column in our data set is a feature. So columns are our features, rows are our observations. A machine learning task has explanatory features and an outcome feature. So an example of an explanatory features is where it says the lender lives or location, country, and then the outcome feature is the loan amount that's requested. Right, so explanatory features is what is fed into a model, and then outcome feature is what we want our model to predict. So outcome feature is the feature we expect to change when the explanatory features are manipulated. These examples, we expect the loan amount to change when we change location. What will the outcome feature and explanatory features be in the research question below? Try identifying some. What will the price overstock be tomorrow? Does this patient have malaria? Will this person buy a car? So these are research questions. If we are to change this into a machine learning question, so the outcome feature might be a regression or a classification. We'll talk about this later. So explanatory features: price of the stock market index today. What we will like to predict is the company's X stock price tomorrow. So the next thing is some travel history, the outcome feature, whether or not a patient has malaria. Income, location, whether or not a person will buy a car. So our outcome features is what we'd like to predict. Our explanatory features is what explains the outcome feature. Yeah. So for example, age, symptoms and travel history, we can use those variables to determine whether or not a patient has malaria. So let's define our explanatory and outcome features for this task. So we have a problem here. I am the mayor of the over 30,000 person town and need to justify spending budget on mosquito nets. I want evidence on how the number of mosquito nets affects the number of cases of malaria. So can you help? So this is a task. So let's start by identifying the research question here. So previously, this guy wants evidence on how the number of mosquito nets affects the number of cases in malaria. So how does the number of cases of malaria change when the number of mosquito nets changes? This is our research question. So the research question is what we want to find out from the data. So one, define explanatory and outcome feature, define the model that you're going to use, that's FX, and then bring everything together. So like I said before, FX is a function that will be used to map our input variables, that's explanatory features, as close as possible to the Y output. That's the outcome feature. So machine learning algorithms are techniques for estimating the target function f to predict the outcome variable y or outcome feature given an input variable x. Those are exploratory features. So from the example we had before, how does the number of cases of malaria change when the number of mosquito nets change? So our explanatory features, we only have one explanatory feature, which is the number of mosquito nets. And what we want to find out is if when X changes, Y changes, right? So if the number of mosquito nets increases, maybe we want to see if the number of people with malaria decreases. We also call our explanatory features X and our outcome features Y, like I said. So from this, we can see that mosquito nets increase the number of we see that when the number of mosquito nets increase, the number of people with malaria decrease. Yeah. So what would you conclude from looking at this data? How many nets would you recommend? Yeah. So you can come to a conclusion by recognizing the patterns in the data. So we can see that the more number of mosquito nets we have, the less number of people, the less number of malaria cases we have. So this is similar to how machine learning algorithm would approach the same problem. Machine learning allows us to learn from history. So if Mr. Mayer, from the example we had no machine learning methods to use, he could find an answer by trying a different number of nets year after year. But this has no obvious human cost, and it will be very hard to update the model to account for example, the new residents in town. Machine learning algorithms help answer questions without these human costs. We are learning from data, or in other words, learning from historical data, right? So human intuition. So over 4 years, from what we've seen, increasing number of mosquito nets decreases the number of malaria cases. So in a machine learning model, this is how we'll say it: an increase in X, that is mosquito nets, which are our exploratory features, causes a decrease in Y, our output features. So it decreases malaria cases. Humans form rules based upon observations and pattern recognition. Machine learning model takes input X and then maps it to the output Y. Okay, our model fx is a function that maps our input x to the predicted y, like I said before. So explanatory features here are a number of mosquito nets. Our model fx, including irreducible error. This is an error that we can't change and it's always there. And then there's the predicted outcome, which is the predicted number of people with malaria. So our goal is to predict y as close to the true y as possible. So this y star, I'll call it y star, is the predicted variable, and then true y is what is actually the actual value of the input variables. So for example, so our function fx maps an input x to a predicted y, which we'll refer to as y star. I'll call it y star. We want to choose a model, that's fx, that will map x as close to the true y as possible. So we want our model to predict, that is y star, to be as close to the true y as possible. Yeah, so basically minimizing the loss function. Like we said before, the loss function is y predicted, what the model has predicted, and minus the actual value. So that's our loss function, which we want to minimize. So we want to make sure our model is as accurate as possible. Right? So, like I had mentioned, E is irreducible error. This is the term that no matter how good your model is, you'll never be reduced to zero. So yeah, here is an example. So let's say we have data with both inputs and outputs. Output is what we want to predict. So in this example, predicted y, which is the blue dot, appears to be close to the true y. We'll talk about how to quantify this in the next section. So the difference between where true y is and where the y predicted is the error that we want to minimize. We want to make sure these two are as close as possible. We want to make sure our model is as accurate as possible, right? So here we see that our true y is really far from our predicted y. So predicted y appears to be far from the true one. This is probably not very useful. We'll talk about how to quantify this later. So what is FX? So FX is the model that we use to map our explanatory features into our predictive features. Yeah. So there are various models we could use. So from our example we had before of mosquitoes, we had our labeled y, and in this case our problem is a supervised learning problem. So the various models you can use linear regression, decision trees, random forests, etc. So this is only when you have labeled data. So let's bring everything together. We've learned quite a lot. So our research question was, how does the number of cases of malaria change when the number of mosquito nets change, right? So our machine learning task is to find out the number of people that have malaria with just using historical data and number of mosquito nets. So the task function depends upon the data type you want to predict. Supervised learning problems fall into two main categories. So there's the regression and classification. Yeah. So let's go back a little bit. So we have machine learning. So machine learning can be divided into two, that is supervised supervised machine learning and unsupervised machine learning. So supervised can then again be split into two. That's regression and classification. So regression problems is when we are trying to predict a numerical value. So for example, we want to predict the value of a house, we want to predict the age of a person, we want to predict, for example, number of people who are affected with malaria, we want to predict temperature tomorrow. So all of these are numerical, thus we go for the regression model. Classification model. A classification problem is where we're trying to predict whether something belongs to a certain category. So either if the email is spam or not. As examples, if this person has malaria or not, if this value falls into massive, or is it a smoker, is it a truck, etc. So regression, we're predicting numerical values. Classification, we're predicting whether something belongs to a certain category. So in this case, we are using the example that we used previously. So machine learning algorithms can be supervised or unsupervised. So this determines the learning methodology. Learning methodology. How does the model learn the function that best maps X to the true Y? So is a model supervised or unsupervised? How does it affect the learning process? So then we check how a machine learning model learns. Overview of how the model shapes itself. We also look at what our loss function is. Every supervised model has a loss function. Like I said, the loss function is the difference between y star, which is the output that's predicted, and y, which is the explanatory feature. And then we learn about how to minimize the loss function, right? So recall that machine learning is a subset of data science that allows machines to learn from raw data. So humans learn from experience, machines follow instructions through the data that's fed, and then learn from experience. So what do we mean when we say a machine learns from experience? It learns from raw data. So remember this tree. We have our research question. How do I have data that may answer my question? Gather or find more data. Do you have labeled data? Yes or no? Yeah. So if you have this is a correct diagram. So if you have labeled data, that's supervised learning. If you don't have, it's a supervised learning method. So what does labeled data mean? Like we've talked about this before. The outcome feature Y. So if you have labeled data, the outcome feature Y you are interested in predicting is recorded in the data. If you have a labeled Y, you can use perfect learning method. If the outcome feature Y is not recorded in data, you do not have a labeled Y, and therefore you go for an unsupervised learning method. So in our example, Y is the number of people with malaria. Whether or not you have labeled data determines whether it is a supervised or unsupervised learning algorithm. Yeah. So if you have labeled data, you go for supervised learning. If your data is not labeled at all, you go for unsupervised learning methods. So most problems we will initially encounter are supervised algorithms. So how do supervised algorithms learn? So imagine you're a teacher and you ask your students a question. The label Y provide the correct answer for the problem and students are trying to solve. Since you know the correct answer, you can reward good students' performance and punish poor performance. This encourages ongoing learning. So students are FX, so they are role models. The machine learning model that's trying to get the correct value. Why? So students are trying to get the correct answer. And since the machine learning the machine learning model or the students have been trained using the correct answers, you should expect them to have an answer at least close to what they were taught, right? That's how machine learning models work. So you can punish the students for answering the answers wrong. You can also punish a machine learning algorithm when it answers wrongly. So you can go back to your data and not punish really, you can feed it more information so that it can get the answer correct. So that the same mistake may not be made the next time. So that's how machine learning models work. And extending this example, you, the researcher, are the teacher and the model of the students. You want to get the correct answer for predicting Y and be the best student in class. So some model, once you've given your answer, you know the teacher will let you know the correct answer. So every time Mr. Model predicts Y, you compare Y to the true Y and see how well he did. So so let me put this a little bit easier. So every time, let's say you have an exam, right? And after the exam, the teacher takes your answers and then compares your answer to the correct answer. So your answers are the predicted Y, and the true Y are the correct answers that the teacher compares. That's the same way model works, basically. Mr. Model starts trying to provide an estimated y by guessing. Right, so here are his guesses. So Mr. Model has predicted 1,340. The actual numbers are 80, 40, 42, 35. So the results appear terrible. Yeah, so these guesses are really bad, judging from the fact that the actual numbers are very different from the predicted numbers. To quantify how good results are, so we use y minus the predicted one. The difference is the error. So from this, which model is useful at mapping x close to y? Bit A is it B? So we can see that fx in B maps x to y star, that's our predicted, much closer to the true y. A loss function allows us to quantify this difference. So this is quite a huge difference between what the answer is and what has been predicted, and this is closer. So we say B is the better model. So our model's goal is to minimize the loss function. So a loss function quantifies how unhappy you will be if you use fx to predict y star. So that's our predicted variable. But the correct output is y. It is what we want to minimize, right? So another way to think about it is what a loss function quantifies how well our fx fits our data. So since I know the right answer, I can compare how unhappy we are with the results. So if the results are bad, we go back and see how we can change the data so as we can minimize the error. So that measure that tells us if we're comfortable with our model or if we are not, it's called our loss function. On the next slide, we will show a few different possible loss functions we can use to assess our model. Because of that, there are two different types of tasks. The regression ones, which we use to predict numerical values, and classification ones, which is used to predict whether something belongs to a certain category. There are various types of loss functions that can be used depending on the type of task. So if it's a regression task, we use absolute error and least squares error. So absolute error is just y minus y star. This square error is y minus y star, and then you get the square of that, and then you add all of it. We'll talk about that later on the next slide. Classification, use log loss and huge loss. So these values tell us how well our model is performing and helps us minimize loss. So there are a few different loss functions we could use from depending on the problem we're trying to solve. So the absolute error is a summation of all we'll take that summation, we'll take the absolute error, we square each and every error, and then we divide it by n. Yeah, that's the number of observations. So if we have 5 observations, we'll divide by n. The least squared error is just y, the true y minus the y predicted, and then square, and then sum of truth observations, and then MSE, the mean squared error, is the summation of all errors divided by n because it's the mean. I hope that makes sense. Yeah, and then there's the log loss where we take the logarithm, the logs, sorry, we take the logs of all the observations, and then the hinge loss, which is not mostly used, but we'll talk about it a bit later. Yeah, so we talked about that. So our outcome feature is continuous. So if it's continuous, it is numerical. If it's numerical, we use regression task, and then we can either choose to use L1 or L2 loss. Yeah. So L1 is the absolute error. L2 is the least squared error. Right. So yeah, here's the formula actually. So fx, this is what is predicted, the fxi, and then yi is our true observed value. We take the summation of that, so that's our absolute error, and then least squared error will have to square it, the square of each error in each observation, so also called L2 loss. This minimizes the square of the error between true y and predicted y. We also have the mean squared error. So the mean squared error, you'll take this, and then you'll have to divide it by, you'll take the least squared error, and then you'll have to divide it by the number of observations that are there. So yeah, so how bad were Mr. Model's initial results? Let's compute the L1. Yeah, so we do 1 minus 80, 2000 minus 40, 300 minus 42, 40 minus 45. And then our absolute error is 2302. That's really bad. So here we are getting the least squared error. So you take each observation, each error in each observation, you square it, and that will give you the least squared error, which is 3 million. That is really bad. And then you can also get the root mean squared error, which is, okay, this is the mean squared error. So the mean squared error, you will take the errors of each observation and then square it, and then you divide it by the number of observations. So you divide it by 4, right? So next we get the root mean squared error. So the root mean squared error, you'll take the error of each and every observation. So for example, case 1 minus 80, we square that, we divide it by the number of observations. They are a total of 4 observations, and then we get the square root of that. So we get 989. So we can compute for each loss function how unhappy we are with Mr. Model's initial random guess. Yeah, so don't worry about these numbers. What's important is if you understand how we're transforming them step by step. So as long as you understand how we compute this. So these are examples of loss function. Yeah, so like we said, root mean squared error is the square root of the average L2 loss per observation. So these are the steps. You get the error, that's y minus y star. You square it, and then you get the sum of all across all observations, and then the mean, and then you root it. So which loss function should we use? L1 or should we use L2? Yeah, so L1 is robust. Is it a stable solution? Not really. L1 is the absolute error. And how many solutions? Multiple possible solutions. L2 is not very robust, but it's stable. And it has one possible solution. So MSE and RMSE are both normalized versions of L2 error. If we decide to use L2, we choose MSE or RMSE. Most of the time, we choose to use RMSE or MSE. The key difference between RMSE and MSE is that taking the roots of RMSE normalizes the error to the same units of measurement. This makes the error term more interpretable. So both MSE and RMSE amplify and severely penalize large error more than small ones by squaring the error. Right? Yeah, so we have classification functions. That's log loss, hinge loss. We talked about the regression functions, which are the mean squared error and root mean squared error, or L1, L2. L1 is the absolute error. So let's define a slightly different task so we can discuss hinge and log loss. this example with the regression problem, where we were predicting a numerical value. In this example, we are predicting a categorical value. So we want to predict whether or not a patient has malaria using their temperature. Right? So we want to predict whether a patient has malaria or not before we're predicting um, so before we were predicting the number of people who will be affected with malaria by looking at number of mosquito nets in an area. Yeah, so that was regression. Here we're talking about classification. We are almost done. We have 20 more slides to go. So our outcome feature is categorical. We want to predict whether or not someone has malaria. This is a binary classification. So the smaller your log loss, the better the model is. Log loss heavily penalizes classifiers that are confident about an incorrect classification. Ways to improve log loss are there problematic errors in the data set. They want to smoothen the probabilities, right? For every prediction Mr. Model makes, we can also measure the hinge loss. So we talked about the log loss. We are now going to talk about the hinge loss. So hinge, potato, is the logical extension of the regression loss function, absolute loss. So absolute loss is the y minus the predicted y, where both y and the predicted y are integers. So either 0, 1. Yeah, so we can't really work with categorical data. If it's yes, no, we have to transform it into numerical 0 or 1. And this is how you calculate hinge loss. So where y can equal to -1 no or 1 yes for each class, or 0 for no and 1 yes for each observation. So the cumulated hinge loss is therefore the upper bound of the number of mistakes made by the classifier. I don't know if that makes sense. So if the true y does not equal the predicted one, the hinge loss increases. Yeah. So if it's, for example, if it's predicted no and the actual value is yes, the hinge loss increases. So we want our hinge loss to be less. So how do you choose a loss function for classification problem? It depends on the question you have to answer. So for a problem where we are trying to assess patient health, we know that false positives, the model predicts you do not have malaria, but you actually don't, are safer and generally more preferable than false negatives. So therefore, it is probably safer to evaluate our output as a probability of whether or not you have malaria. So you use log loss. So that's an example of how you would decide which loss function like to use for a particular problem. Note on classification loss function. Provide only a broad conceptual overview of log loss and hinge loss, as we will not be using them in the coding lab, so I'll share the notebooks later. However, we encourage you to explore them further on your own. So how does our model improve on its initial guess? That's what we're going to talk about next. Our initial root mean squared error is very high, as we have calculated. That means WAC. So let's try using a different model that compares and then compares our RMC. So if the new model reduces loss, the model keeps changing the fx that direction. After every change, he measures whether the loss has increased, decreased, or stayed the same. Yeah. So the process of changing fx to reduce the loss function is called lines. It is so it's not changing your model; it's changing the values in your model. If that makes sense. It is what makes ordinary least squared regression or machine learning algorithm. So for every fx we choose, there's an associated loss, right? So the learning process involves updating fx in order to reach a global minimum loss, so like the most minimum loss that you can get. Yeah. That's so. If you've ever had a gradient descent, that is also an example of gradient descent. So Mr. Model sets the random fx and updates fx to make our loss as small as possible. So our goal is to make the error to be as small as possible. So Mr. Model succeeds when he reduces the error to its minimum, to its minimum. Yeah. So as you can see here, that's where we want our model to be. So what if we don't have label data? You can see slides. Okay, this thing is yeah.
Not crazy, yeah. Application
But I checked. Um, so I guess this one was being shared. Sorry about that. I'm not sure about this. Iko na kina iko na kitendela, iko na weekends, iko na Rugamboko pia alikuwa na namba ya $100. What's the inflation in Kenya? So what if we don't have label data? If we don't have label data, that's an unsupervised model. So when does the model stop if we don't have label data? What happens if we don't actually have Y data? So we turn to unsupervised learning techniques. So unsupervised learning does not have label data. However, it is the most promising current area of research. So for every X value, there is no Y. We do not know the correct answer, so we cannot act as a teacher. Instead, we try to get an understanding of the distribution of X to draw inference about Y. Why is unsupervised learning important? So a researcher made an analogy that if intelligence was a cake, unsupervised learning would be the cake, and supervised learning will be the icing on the cake. We know how to make the icing, but we don't know how to make the cake. Unsupervised learning is the holy grail of machine learning. So to reach true ML needs to get better at unsupervised learning. So humans learn mostly through unsupervised learning. We absorb vast amounts of data from our surroundings without needing any labels, right? So here's an example of an unsupervised learning model. So example, social network analysis. So in a social network, clustering can be used to find users that interact a lot with each other, say through emails. This is shown by the figure below, there are users where the users have been clustered into 4 clusters. Yeah, as you can see, there are 4 clusters. So here we don't have a why, we just get inferences to what we have. So the clustering algorithm uses email patterns to predict the hierarchy of a business organization. So based on email interactions, we are able to see who the boss is. So what is the performance measure for our malaria net example? So our malaria net example was a regression problem. So our task was to accurately predict the decrease in malaria cases for a given increase in mosquito nets. Our performance measure was the mean squared error. So our next measure, what's the performance measure for our malaria patient example? Our second example was a classification problem. So the task was to accurately predict whether or not a given patient is likely to have malaria given his or her temperature. In the next class, we're going to do model selection and evaluation. I will not get through that today, but I will share links. I will share a link where you can access each and every resource on our GitHub. So yeah. Thank you so much for joining me. I'm sorry about the technical issues. Hopefully next time we'll have a better live recording. Cool.